Okay, so in the last video, we started talking about optimization problems, applications, and using the first derivative test to actually solve that optimization problem out. Now I just want to go through a few more examples so you can see some more worked out. And like I said in the last video, I'm deliberately doing applications different than the ones in your book because I want to give you as many different examples as possible to see so you can kind of get an idea of how to work these things out. So, the next one we want to look at, let's see. Okay, there's a lot of, in the same way that with related rates, there's a lot of standard types of problems. Find the rate of change of a sphere. Bear with me, my cat's going to launch herself. There she goes. Okay. There's a lot of standard problems. The rate of change of the volume of a sphere, the rate of change of a cylinder, things like that. Those troughs, those trapezoidal troughs with water flowing into them and all that. They're standard related rates. There's a lot of standard type optimization problems that, again, I just think are really fun. So I want to go through a few of them now. So suppose we say we have this, and I just want to use the same numbers I have in my book. Okay. I am fencing a rectangular pen. I have 100 feet of fencing. What is the maximum area I can enclose? And again, we said last time, first step overall, determine what it is you're doing. I'm told to find the maximum, which means I'm doing optimization, which means I need some function to optimize. What is the maximum area I can enclose? So I care about area, and this is a rectangular pen, so the area is easy. Length times width, or x times y. Use whatever letters you want, it doesn't matter. But then the problem is, we said there's two variables here. Y is not a function, they're both variables. In order to solve it, I need to write it in terms of one variable. And also for a lot of these, much like with related rates, since they are geometric problems, draw a geometric picture to get an idea of what's going on. It's a rectangular pen. And if the area is x times y, call this x and that y, it doesn't really matter. And the other thing I'm told is I have 100 feet of fencing, which means the perimeter is 100. But now we all know the formula for the perimeter of a rectangle. Perimeter equals 2 times L plus 2 times W, which in this case I can substitute in. I get 100 equals 2x plus 2y. And now, this is the function I care about maximizing that are going to differentiate. I use this to eliminate a variable there. Pick a variable to solve for. I think in the last one I solve for x, so I'll solve this one for y. Subtract the 2x. Divide the 2. Now I have my relation. Plug it in up there. And we'll switch colors just for the fun of it. Then we'll go right over here. And we get area equals x times y, which is 50 minus x. So area equals 50x minus x squared. Now I have my function. Switch colors again. Now since I want to maximize this function, take the derivative. A prime equals 50 minus 2x. Now to get the maximum, first derivative test, we find the critical points. Set it to 0. 0 equals 50 minus 2x. Add the 2x, divide the 2. You'll get x equals 25. Again, as I stressed before in the last video, you can throw this into the sign chart to make sure it actually gives you a maximum. It will, so I'm not going to take the time to do it. But now, if x is 25, y is 50 minus 25, so y is 25. And then two things. I am not told to find the dimensions of the maximal pen that I can get. Sometimes you will be, so I'm done. Here I'm told to find the maximum area. So what's the actual maximum area? 25 times 25. So the area is 625 feet squared. And I stress that, just make sure you answer the questions you're asked. If you stop right here, you haven't actually answered the question, so you're going to get it wrong. So make sure you answer whatever the question is tells you to do. The other thing to think about here, I'm told it's a rectangle, and from a real world perspective, if I have a rectangle and I have 100 feet of fencing, what would be the best shape to create? Well, according to this, something that's 25 by 25, a square. And if you think about it, that's just logical. The best way to divide something up and have it be the maximum you can possibly get is to have the length and the width be the exact same, which turns out to be true, which to a certain extent can make these problems a little bit not as fun, because it's pretty obvious. The best rectangle I can create is a square. Okay, good. Just divide that by 4 and I'm done. But, like I said, I like these problems because you can really mess around with them a lot. So, let's see. Suppose we have this. I have no idea. We'll go with 120 feet of fencing. Let's see. And now, I'm not going to write this in words because it'll be too complicated, but we will say I'm going to create a rectangular pen, but I don't want to keep track of the animals that I'm going to put in that pen, so I'm going to have the pen next to my house, meaning my house is right here. I need to make my house bigger. My house is right here. There we go. And the pen is going to sit next to my house, which means my house forms one border of the pen. What is the maximal area I can enclose, and what are the dimensions that will give that maximal area? This problem is clearly the same but different as the last problem. Well, let's see. I can still say x and y for length and width. I still want to maximize the area. So area is still x times y. But now I need a way to relate x and y. And clearly we can use the same trick we did before. I have 120 feet of fencing. That's the perimeter. So the perimeter equals 2L plus 2W. The perimeter is 120. But the problem here is that's not actually true. The perimeter is the length around your shape. But in this case, I'm only talking about the fencing. This rectangle only has 3 sides. That side is bordered by my house. A lot of times in these problems, you'll do that, or you'll border it by a river or something. That's why we draw pictures to get an idea. But it means I have to alter this. My perimeter, if I just label the sides, is 2x plus y. There's only one y. But now, I still have an equation. I'll solve this for y since it's easier. Y equals 120 minus 2x. Now substitute in over there. A equals x times 120 minus 2x. So that's 120x minus 2x squared. Now, I do the first derivative test stuff to find the maximum. So I take the derivative, 120 minus 4x, set it to 0. Add the 4x, divide the 4. You get x equals 30. Again, I'm not going to take the time to check that that is a maximum with a sign chart, but I could and it would be. Now, if x is 30, y is 120 minus 2 times 30. That's 120 minus 60. And y is 60. And now we saw with the last problem, a square was the best, most optimal shape we could create for our rectangle. Here, now I actually get a rectangle, not a square. And it's essentially because one side of this pen is not getting fenced, so it makes more sense to have this dimension be twice as long as that dimension. So now, let's see, we said I wanted my dimensions, there they are. We also said I wanted the maximal area, but the maximal area will be 30 times 60, which is 1,800 feet squared. And again, like I said, I really enjoy these problems because, well, they're somewhat fun to draw out. Even I can draw a simple picture to make this work. And the answers you get are logical if you think about them, and then the math actually backs that up. So one more. I'm actually not going to solve this one out. I'm going to leave it to you. And then feel free to text me the answer after you watch the video and figure it out. But suppose we do the same scenario. My perimeter will go with 200 feet square, 200 feet of fencing. This time, the fence is going to be bordered by, the pen is going to be bordered by a river. And rather than writing it in English, I'm just going to draw a picture of it because it'll be easier than writing all the words out. There we go, right there. Now, I don't want one pen, I want 3 pens along the river. Each one has to be the same size. So if you will, call this A. If you want to call them A1, A2, A3, you can. But I want to know the dimensions that will maximize the area of each of those pens, keeping in mind all the pens are the same size. I may not look it with the way I drew them here. That one looks like it's the smallest. These are all the same size. But can you come up with an equation that you can solve? If I want to find the maximal area of, say, that and that and that, I could maybe do something like the area is equal to, well, I don't want to give everything away, but how am I going to label my dimensions? Well, if I call this X, what do I call Y? There's different ways to go here. If you want to call the whole length Y, you can. Like I said, I'm going to leave this up to you. If you want to call each individual section Y, you can. But clearly, the area of one of those pens will be X times something with a Y in it. You'll then need an equation that will allow you to get rid of one of those variables. But you have 200 feet of fencing. And again, do the same thing. Label the sides. If this is X, this is X, this is X, this is X. This will change based on how you choose to do it. Either you'll have just Y, or you'll have Y plus Y plus Y, based on how you choose to set it up. But then you can do something like the perimeter, which is 200. So 200, for the sake of mine, just for the fun of it, I'll say 4X plus, I'll say 3Y. Doesn't matter. Leave it up to you. There are different ways to set this up. Try to set it up multiple ways and see if you get the same answer. But the goal is to find the dimensions of the maximal rectangle pen that you can make, and there's 3 of them, they're all the same size, and the actual maximum area. Like I said, if you can set it all up and solve it all out and get an answer once you do this video, email it to me, call me, text me, let me know. See what you come up with.